lectures 39 and 40 on thermodynamics of materials. Please note that last day's class was of 2 lecture duration. So it was, I initially wrote 38, I'm sorry, 37, but it should be 37 and 38 as I have noted here. So last day it was 37 and 38, 2 lectures, and today also 2 lectures, 39 and 40. Note this. So with this, so I will continue with this. I will first finish this, and then I will take up the assignment, the remaining 2 problems on assignment number 4. This will be actually we will cover. Then we will take up the next chapter or next topic. So this is the planning. So first finish what I try to just recapitulate what I said. What I said, this is the topic: entropy, disorder, and probability. This today entropy directly S, not delta S. Delta S is defined in classical thermodynamics as ds or delta S, as dq reversible by t. No S, directly ds coming. If you integrate, then there will be constant term. So absolute definition of entropy you don't get from classical thermodynamics. So you want to get it if you, this is the statistical thermodynamics, statistical interpretation of entropy. So I would say, actually, so this is statistical interpretation of entropy. Achha, statistical interpretation of entropy. Mark the word entropy, not entropy change, of entropy directly, of entropy. This I will cover as much as possible, only short, time limiting. So configurational entropy change particularly, I will actually have to leave aside. So maybe I will be take back if time permits later. But till then I give you the reference, so that this part you take from Gaskell. Okay, reference Dr. Gaskell. Come in. Dr. Gaskell, or page number, please give me this page number, okay? Just 40, last two, yes, page number is 73. And last page, give 89. Page number 73 to 89 for detailed study. I'll give you outline, that too not configuration entropy change, this you will get there, but time, if I get time, I will cover later. So this is second edition, this page, second edition. My book is little old, this actually now runs 4th edition, 5th edition, you check this, okay? No problem, the standard. So let us recapitulate what I discussed last day, what I said last day. Topic being entropy, disorder, and probability. I wanted to establish this. We wanted that entropy of gas is greater than entropy of liquid, and that in turn greater than entropy of solid. So solid is least, and right, absolute entropy. So, this has been shown yesterday by this classical relation. The integration I showed somewhere, integration of this CPDT with including phase transformation, all these things I showed. This is the domain of solid entropy, this is the domain of liquid, and this is the domain of gas entropy, means gas entropy is greatest. This we discussed. And we also understand that disorder in a structure is greatest in gas. Molecules are not fixed, actually they are always moving around. So disorder maximum, solids are confined to a point, lattice point, and vibrating only. So least, and it actually stands between them. So this is the this is the order of disorder. So we say conclude entropy maybe is a measure of disorder of the system. This we discussed last day. And also in this context, we should note that star use the term mixedness, and according to him, entropy is a measure of mixedness of the system. Okay. And this is disorder of the system, mixed upness of the system. Now, I begin today's discussion with this. So remove all these things now. So I start with this Botzmann equation. Botzmann Botzmann equation about entropy is what? S is entropy, direct, absolute entropy is K ln omega. This is a omega. What is omega? Omega is, this is Boltzmann equation. S is the entropy, as you know. K is the Boltzmann constant. Boltzmann constant, okay? Boltzmann constant. And S is the entropy. Omega is the interesting parameter. Omega is what? I am giving variously known as, we are into the domain of, we are actually discussing statistical thermodynamics or statistical interpretation of entropy. Statistical interpretation of entropy. This we are discussing. So, not classical. Classical, you know, you are completed. As entropy change. Classical completed. Today, all statistical discussion. So, omega is a statistical term. Okay? It is variously known as. So, remember this. This is actually. You can write this statistical thermodynamics. Statistical thermodynamics. This is we are discussing. Entropy as delta S as ds is already covered, is already discussed in classical thermodynamics. Discussed in classical thermodynamics. But I'll show at the end that there is no conflict between these two. This is getting insight. What is entropy, sir? What is entropy, sir? So you hear 100 times, million times, whole life. So, so it is better we touch upon this. Sigma is variously known as degree. I am keeping on writing of disorder. Okay, as I already degree of mixed upness, as Gibbs said, mixed upness. Still, complexation is another term. Complexation is a statistical term. Complexation, statistical distribution. Statistical means statistical distribution. How many ways you can distribute? How many ways I can distribute these four guys here? Okay, I can sit him here, then I can sit him here, he can be there. Then okay, you are two square. Then giving the fixed value here, then you come here. So you say 4C2 or 4, okay, so 4C, okay, these things, okay. It can be considered, okay. This, yes, combination principles, combination relationship will come here. Okay, very good. How many distribution? That gives an idea of entropy. Okay, so mixed termness and what is else? Complex sense. This is statistical terms. And another is very helpful, number of microstates corresponding to a macro state given by internal energy volume. State, macro state means state, what you know classically, that state. So this is how many micro arrangement possible with the given macro, one macro fixed, how many micro? This number is omega. Last. And last is probability. Entropy is a measure of probability. This is your omega. See, okay? Macro state. See, I tell you, have you read resonance in chemistry? So one structure has many different arrangements. That concept. How many resonating structure? So here, how many resonating microstates for giving macro state? So greater, more resonance. What you understood? More resonance is actually more stable. Here also more microstates. Okay, then it will be equilibrium state is the most stable, and that has the maximum number of microstates. So there is some correspondence. Okay, so I'm trying to give you some analogy so that it encourages you. Okay, no, these things. Okay, so number of microstates. Okay, I'll give this. So now I tell you. Now this actually we have two types. Classical, remember, don't mix up with classical. Classical over. There is two types: S thermal, S thermal plus S configurational. Two together. Thermal is what? Thermal what? S thermal is what? You tell me. K ln omega thermal plus K ln omega configurational. Thermal configurational. Happy? Very happy, I guess. Huh? So you can write also if you are interested. K ln additive means multiplicative. Ln add means multiplication. So ln omega thermal times omega configuration. Sorry. Okay, very good, very good. Very best. Okay. Now what is omega thermal? Now next step, I tell you what. Omega thermal and omega configuration. Configurational. Configuration or thermal configurational. Okay. So thermal, the number of ways it arises out of this the number of ways the available energy means you say a constant internal energy may consider. Example, internal energy. Available energy can be shared, can be distributed, or can be shared or mixed up. I'm using Gibbs phrase. Mixed up also. Can be shared or mixed up. Share, distribution actually, mixed up among the constituent particles. Particles means atom, electron, okay, this. Among the constituent particles. While configurational is what? Configurational is what? Again, similarly, arises up. So arises means this. Why this is not S thermal? Okay, this is arises out of this. Okay, no, I'm sorry. Achha, very sorry. Number of ways. Okay, okay. It is number of. It is given by the arises. Actually, entropy arises. Entropy arises out of omega because it is not entropy. This is not same. Separated by ln then k Botzmann factor. So this is exactly this. It is the number of. So entropy arises. And what is the configurational? Again, it is the number of ways the particles can be distributed or mixed up. I am still using mixed up language. Mixture. Over the space available to them. About the space available. So that means how many space, 3 dimension. Yesterday I was saying crystal. Last day I was considering crystal, metal crystal vacancies. Vacancy inside here, vacancies. How many here or there? Atom and vacancy combinations. Okay, how many ways? Configuration. I wrote there also last day. Configuration. That's why this is about particle, sitting of the particle, placing the particle. No energy. How many ways? You sit. A moment ago, what I said, you can be here, you sit here, etc. This is configuration, not thermal. Thermal is about energy. So 3 joule of energy. How many ways I can distribute over the energy level? Energy level is what? Quantum level. Quantum. Statistical, of course, uses quantum theory. Quantum levels. This I will give this example. I will discuss actually this. So, okay, today we will discuss. Today we will. Okay. Today I shall explain what is this called? S thermal entropy, S thermal or omega thermal, with the help of an example. With the help of an example. Presently, the help of an example just now. Okay, and S configuration will be taken up. S configurational will be configurational entropy. Configurational entropy will be taken up. Okay, later, time permitting. Time permitting. Otherwise, time permitting, or you may refer to Gaskell. You may refer to Gaskell's book. Over, this is okay. So this is my planning, okay. So you understand the way. So let me complete this. Thermal. Suppose, consider a state, a system at a state, is at a given state has 6U energy of 6U, as energy of 6U. U is the internal energy, plus 6 for distribution purpose I have written 6. It can be, okay, U, okay, then you do fractional distribution, okay, 6U, joule, unit, joule. Now let us say what is thermal entropy. Distribution, 6. Now there are, see, you follow this, these are the quantum levels. Achha, by the way, I tell you what, something. Achha, one principle, as I go on, this is solid, say, for solid, 6U I am distributing over the quantum levels. This is the quantum E0, E1, E2, E3. These are quantum levels, energy levels, quantum levels, energy levels, okay? Quantum levels. What is the energy here? I am giving 0, assigning 0. This is U, this is 2U, this is 3U. And also note and also consider here 3 particles available for discussion. For example, I also consider 3 particles. 3 particles available, present. Also consider 3 particles are present over among which the energy will be distributed. The given energy 6U energy will be distributed. Very easy. Let us try. 3 particles. I am assigning. I have 3 particles, 1 arrangement. So I am giving a number of arrangements, so you will easily follow me. First arrangement. I am giving 2 particles. See, follow 2 particles, which 2 atoms? Here, 6 and 1 there. 0 level. 0 energy is actually no. 0 energy is actually sometimes, okay. Harmonic oscillator don't, okay, consider this, okay, and 0 level half kT. Half h nu, etc. But 0 is available in the, okay, see, energy level of the electrons, okay, Remember atom, electron structure have at the infinity energy is 0 and towards the nucleus gradually negative, all negative values. So don't worry. Oh, sorry, don't worry. So this is one distribution. Second distribution can be what? Very easy distribution. 3u, 2u, u, 6u. Okay, still another one, 3 particles. Still a simple way I am actually representing this. So this will be good enough. This is actually a lifelong study. Statistical interpretation of entropy is a lifelong study. But one thing I should warn. Some people talk about only statistical interpretation of entropy. But you full know actually the classical is actually already self-sufficient. It has covered everything. And if you have any this type of problem, today's problem or other problem, which subject you will which branch of thermodynamics you will resort to? Obviously, this one, classical thermodynamics that you are studying. What you are studying, classical. So, what's the use of number of waves? I will get this. What is number of waves? What is the adiabatic flame temperature? With the classical. So, this is good enough. Okay, but some people actually talk about etc. But I think the useful thermodynamics is the classical thermodynamics. Classical thermodynamics is thermodynamics. Remember, I said. But still, you have to discuss because a lot of things are about, particularly in terms of entropy. And entropy is inbuilt in next state functions, namely G, coming today, gives free energy. So it's inbuilt there. So entropy is an important issue. So that's why we are discussing. Okay. So these are another is what you know. What is this? We can get this to how many distribution? 3 distribution. That means you can write omega is what? Omega is 3 distribution in this arrangement. 3 distribution. Okay. 3 distribution. Okay. I don't know. I'm writing 3 distribution. This. Achha, when it is considered liquid, can I remove this? This part? Can I remove this part? Liquid I am considering for some reason. Now, yes, what is the purpose? To show, to establish 2 things. One is solid is entropy is contrasted with the liquid entropy, which you know, recall, we know what? Liquid has greater entropy than solid, or say gas. Gas has greater entropy, much greater entropy than the solid. This we know. This I will actually show here. In one extreme is solid, another extreme gas. So gas, same metal, same gas. Now you see, interestingly, this is the quantum energy levels. This is called what? This is called, in the language of quantum theory, forbidden energy gap. Forbidden energy gap. You cannot assign any energy here. Nothing there. Very good example of quantum theory. Ladder. You know, ladder. Stand a ladder here. This rung, this rung, this rung. You cannot stand either this rung or next rung. Not in between. This is the quantum level. So, another thing. So, either this or that. No, you can get this. So, gas, I'm redistributing. Gas actually available energy levels are increased. Why? Gap is decreased. Forbidden energy gap is decreased. Means this here particle in a gas can have access to has access to more energy levels. Why this happens, I tell you what. More energy levels, why this I am telling. See, you know, one principle of quantum theory is that if a particle is confined, then its energy levels are quantized. It's confined, cannot move freely. Don't move freely. We are also, we can be confined. Then energy levels will be quantized. Quantized means forbidden energy gap will show up. What is the opposite of quantum? Okay, this forbidden energy gap and this quantization, what is the opposite? Continuous. Classical, Newtonian. All energies. In high school, did you say, now this energy cannot be acceptable? Any energy, including 0. Okay, sir, this 0.1, 0.2, what is the kinetic energy? All. So, continuous, as different from, as opposite from quantized. So, we are discussing quantized, but this will be now gas, since restriction is greater where? Solid or gas molecule. Restriction is, movement restriction is where? Greater. Solid is much greater. So, his quantization is forbidden energy gap is greater. So, these are the quantized levels. Quantum levels, okay? Quantum levels, okay? Quantization has occurred. Since gas is free, much more free to move around, so its energy levels will be space or forbidden energy gap will be reduced. So what it will be? So between these two, you have to insert another one. Between these two, and between these two insert another one, and between these two insert still another one. What are the values assigned? Zero energy, this half u, this is u already u, this is 1.5 u already. Now this is 2u already, this is 2.5 u. Now this is 3 u already. So insert. So now see, forbidden energy gap has been reduced as characteristics of gases. Gas molecules are free to move around. So free means, so if we reduce further, what it will be? Reduce further, narrow the gap. Then in the limit it will be all levels, continuous energy levels. Okay, that you will see all value. So half u was not accessible, but now it is accessible. Now you do this what? So given this condition for gas, okay, what is this? This is actually, gas is actually forbidden energy gap reduced. What is the reason? Because gas molecule, so write this, reduced right here, because reduced because gas molecules are gas particles, gas molecules, okay, are more free to move around in the system, in the container actually, in the system, okay, in the container, I'm writing in the container. System is general term, in the system, leave it there. Okay, but this is, okay, forbidden reduced here, gas molecules are, okay, gas molecules, atoms are particles, atoms, solid we don't write molecules, atoms or particles are have restricted motion, have restricted movement, confined movements. Just write this so you understand. Hence the quantization. Okay, forbidden energy gap right here. Forbidden energy gap. There's a movement. So forbidden energy gap, right? Forbidden energy gap is greater. Is more quantization and greater. So write here. So I can write here also. Energy levels are more quantized. Top. Energy levels are more quantized. And what you write? Gas energy levels are less quantized. Or energy levels are quantum levels are less. Energy levels are less quantized. So all I have written, all property, it begins with the confinement. See, particle in a box, I tell you, the story begins with the particle in a box in physics. A great theory. Particle in a box, study this. 1 month study this topic, okay, particle in a box. So this is actually box. So very good. So now I can see. So what has happened? I'm not see these three already there. Here also already 3 plus additional. Additional is how many? I'm doing this. See, I'm trying 1, 2, 3, 4 perhaps. Let us see 4 perhaps. Okay, let's try. So 1 I'm trying. 2 particles, 2.5, 5, and 1. You all set. Still another 3, 2.5, 5.5, and half. Okay, 2.5, 1.5, 4, and then another 2. Already 3. Another round will be, you just find this out. Six, you have to make it 6 actually, you know. Oh, this is possible, no? This is possible. Here, oh, this I have already 5. And this, if you give 3 here, this is possible. This is possible. This is 2 particles. 2 particles. So how many arrangement extra? 4 now and 3 already. It can be this. So it is arrangement is number of distribution. So right here, number of distribution. So write omega here. Right here omega. Right here omega. 3 omega. Omega distribution is omega. Number distribution is what? How many? How many is 3 before? 3 already. 3 already. Plus, hello, what are you doing? Plus 4 now. What is this? 7. Which are omega getter? Which is omega getter? Gas or solid? It is 7. And entropy is related to omega, number of arrangements. So entropy of gas, no surprise, is greater than entropy of solid. This is the explanation. Classical explanation, you see, the relation I gave you last day, domain, solid, liquid. Classical is fantastic. But this is here, you see, number, where this is arrangement, okay. So this is your statistical distribution. So this is, so hence, since right here, since, let's start this 7. Since distribution omega, which is distribution omega, what type of omega it is? Thermal or configurational? Thermal. Energy is distributed over the levels. That is spatial, space, sitting. Where are you sitting? Here in the space. Like crystal lattice. Where? Here or here or here. See about sitting there. No energy. So this is. Number of distribution?
How did you calculate number of distribution?
The distribution is 1, 2, 3. This distribution possible to micro state. Corresponding macro is 6. This is the macro state. One distribution. You what? With 2 particles in the 3 level, 3rd level, E3, and another is first level, first quantum level. Okay, E1 level, say PMS here. So this another is 1 here, 3rd, 2nd, 1st. This is another distribution. Still another. Very simple presentation though, but 3 distribution. And here also 6. You have to make up 6 because that is the macro state, right? This is the macro state. This is the macro states. I told you what is the omega? Number of micro means these are the arrangements. Micro, you know. Microstructure, you know, physical chemistry, metallurgy, microstructure.
For solid C is 6 and for gases 4 is 6.
Can be? No. Avogadro's number of particles are there. No. This is example. I have given. Consider an example. An example I have written somewhere. An example. No. In general, greater I am saying. Tell me.
There can be more arrangements.
Of course, this will be more. Avogadro's number of arrangements you have to consider because Avogadro's number of particles are there. Okay. Yes. And moreover, these lattice sites actually also and maybe consider. I have not considered. Okay, whether this point or this point A said this I have not. Particle I have considered. Particles are actually indistinguishable lattice. These other complexities I have not considered. But this is an example with 3 particles, see, and 6 energy, 6 U energy. I am giving this total energy. You see. With solid and this, actually more, okay. Greater, actually, this energy, if in the gas phase, number of distribution is there, okay. Typically solid and gas, it may not be this actually solid and gas. So oxygen, this is say iron. Iron and oxygen. With having 6 this energy, so this how many distribution of gas? So this 3 and here 3 plus 4, 7. So distribution, what distribution? Sigma thermal. No, it is not fixed. Solid means 3 distribution, no at all. 3 particles are there.
Are we talking about the possibility of distributions in this?
No, this is the distribution. Possibility. Possibility is what? Probability is actually possibility of distribution means okay. This can be this can be this can be this. This is possible. Okay. Total. If you see, actually, total is how many here? No. See, I'm telling. You tell. Suppose 7 here. 7 though. 7 here. Actually 3 here. This distribution, what is the probability? This distribution 1. Here, this distribution. 2 here. What is the probability? 1 out of 3. Here in the solid, 1 out of 3. This is the probability. This can be here, can be there, can be this. This is probability. This is probability. Okay, this is the probability. Total is 1. And here also 1 out of 7, 2 out of 7, etc. So this is the probability. Well, yes, anytime it can be here. This one. Okay. But this is actually no. This is total is this 1. Now this is also 1, no? This is 1 also. This is also 1. Okay, 1 of 3, 1 of 3, 1 of 3. This is the way I have said. Actually, this can be given actually with the lattice arrangement. Okay, probability will also change. Okay, this have to actually I have to include more actually lattice factor. Actually, bring in the lattice factor and lattice sides. Okay, A, B, C sides. Maybe A, B, C. This I have to actually think. But later anyway, so distribution sigma thermal, what I intended to, that gas has greater entropy than solids. This is one thing I wanted to intend. And what else? That is, what is configuration, thermal entropy or configuration entropy for the matter? Distributions, okay? How many ways in a macro state can have how many micro states it will be? It will be there, okay? This is. This is actually all individual, probability same. This is not 2, probability not 2. Okay. So you can, this is actually, see, each are 1. See, you say each 1, 1, 1. 3, 1, 1, 1. Same probability because as possible, as probable as this. These are equally probable. Okay. So distribution is what? Sigma thermal. Distribution is what? Thermal is. So distribution is distributions are greater. This is my, in case of gas phase, greater than in case of solid. So distribution, okay, probability which is more probable, equally probable. These are equally probable, okay. And also you cannot compare this with this because this is separate thing. Gas, if it is gas, there are energy levels. So I am showing if energy levels increased, quantum levels increase. Available energy levels increase means more distribution, and more distribution means omega, and more entropy. This is the message. This I wanted to do, but about the probability. Then in case of, okay, probability actually I could have explained this if a time permits. I have said configurational entropy change I will discuss. Then I will show you actual probability. Okay, so given the initial state, how many ways they can stay and what are the probability of this. See, I tell you, chemical reaction equilibrium attain. Equilibrium state is the most probable state. I mean the greatest entropy. So this is the probability. Omega probability. Omega maximum, S maximum. This I can show you actually. Let me finish this. Of gas, then in case of, if you bring in probability. Okay, probability I cannot tell you here. Probability actually I cannot tell you. I can give you what is the probability, equal probability if you ask me. Here equal. This I cannot distinguish. But probability I could have given configuration. This I am not considered. Actually, I may give little bit of outline since you asked this question. Probability I'll tell you quickly. So distribution are greater in case, hence what is your comment? Hence S entropy, S of entropy of gas is greater than S of solid as already decided predicted classically. So there is no conflict. Okay, I tell you another thing for your benefit. See here also note here, star, double star. Note this I will help you. Say this is S, double star. Achha, what is this? If it is S, delta S is what? Delta S is what? Tell me. S is this. Delta S should be actually, see, S is the thermal and configuration, as I said. So at a given state, so initial state, thermal configuration entropy is total entropy, and final state. For example, can I remove this? Let us say. Gas, initial, final, you know very isothermal process. I don't, I'm actually, anyway, this is important topic. V2, S2 minus S1. Delta S is, so S2 minus S1, S2 directly is what? K ln omega 2. Distributions of particles in this state and distribution of particles, gas molecules, here gas molecule, ideal gas. N moles, ideal gas, isothermal process. Okay, okay, isothermal. So N moles ideal gas. What I am writing where? Okay, N moles ideal gas. So yes, S2 minus S1. So S is what? K ln omega means probability of this state or say number of microstate in this state. Okay, omega 2 minus K ln omega. You will get where it is actually degree of mixedness, etc. You will get this actually, you can obtain from this actually omega 2 and omega 1, get this result. It will give you, this will be same as delta S obtained classically. This will be same as this is, they are the reconciliation, no conflict. Actually classical thermodynamics you count on, and it must comply with that. This will be the same as delta S obtained classically. What is this? What is the value? Tell me. That is RTLN. Tell me. Delta S obtained, RLN V2 by V1, recall. RLN V2 by V1, isothermal, delta S RLN V2 by V1. So this you get, okay. These here omega T number of distributions, okay, probability, okay. Then actually distribution. See molecules, how many quantum states will avail here? See this is a compressed state. This is an expanded state. In which case you have say, see here in the language, this is key, positive or negative first of all, classically positive or negative. V2 V1. Entropy increases in this. So here, see this to this. Entropy here and here, it is squeezed. As a confinement, more confined. So more quantized, forbidden gap. So any energy will be distributed here actually, less distribution, greater distribution. Omega is less, omega greater. Positive. And can be shown exactly. So this is actually there is connection is there. Another thing that you are talking about the probability suddenly, this is also, so write this, considering the probability, remove this, let me complete this. Considering the probability, what we can say? With respect to probability, what I can say? Probability, okay, what is this? The state with maximum entropy. The state with maximum entropy. I say follow here, everything here. Only two types of thermal and configuration. Thermal I have shown, configuration is actually about space. with maximum, the state with maximum, what is this maximum entropy? Entropy is the most probable state. Maximum entropy is the most probable state. Example, e.g., in a chemical reaction, which is most probable? A chemical reaction occurs, the equilibrium state, then in non-equilibrium, it starts, then number through non-equilibrium, then reaches equilibrium. So equilibrium state has the maximum number of, has the maximum number of okay, so what do you call actually microstates? Actually, equilibrium has a number of microstates or complex sense microstates, and has the maximum entropy. I'll show you. And hence the maximum entropy, and hence the most probable state. That's the equilibrium. Entropy, classical statistical thermodynamics says what? Why equilibrium occurs? It says, I tell you the difference. It says that is the maximum entropy state. All chemical reactions tend to equilibrium. Stop here. What is classical saying? Classical says free energy is minimum, which I have not addressed yet. Gives free energy of the system will be minimum. It says that has the maximum number of micro arrangement. Equilibrium, they have non-equilibrium states have also micro arrangement, but they are not as many as equilibrium. So it is 100. They have 90, 80, 70, 10, 5, 2, 1. Initial state. Non-equilibrium. So moves on like A plus 2 reaction you have said. A plus 2B goes to 3. I'll show you this. Okay. And hence most probable state. So the equilibrium state has and hence is the most probable state. Most probable. I should actually address, I'm showing you, you'll be interested. Right here only, in a isolated system better, in a constant internal energy, constant volume system. You write this, you know what is this? Internal energy system, isolated system. I'm showing you this, you will understand very easily. In equilibrium, I have not addressed. Far away from equilibrium. This I say fugacity, activity, many things. I have not started yet. So what I see here, this reaction, so you are taken in an isolated system. This is metal plus oxygen, metal oxide. So what is this? Isolated system. Isolated system. What you have taken initially, you have taken A and B. A and B you have taken. So what it will go to? It will go to initial. It is 3B, 4B, 100B, anything. Don't have to be stoichiometric. It may be stoichiometric. Okay. Initial state. Write this. This is what? It is equilibrium state. I said what is the spontaneous process? System moving from non-equilibrium, initially non-equilibrium, that is chemical reaction. Or two bodies at different temperatures contact with non-equilibrium. To equilibrium. Equivalent to irreversible, but that is subtle difference. Initial is non-equilibrium, but irreversible initial is equilibrium, at least. And finally is of course equilibrium, and intermediates are non-equilibrium. So this is spontaneous process. Chemical reaction, spontaneous. Initial state, sorry, remove this, initial state. Very good. So what is this? And this is isolated system. Now this is moving state, initial state. What is the state I will write? Non-equilibrium. Non-equilibrium. What will do? It will react. React producing what? Tell me. What will do? Produce C. So A be unreacted, C. How many are, that depends upon the equilibrium constant. Don't worry about this. This is the equilibrium state. I'll show you this. This is what? State 2. Initial state 1. State 1, state 2. What is this state? Equilibrium state. What has happened? What has happened here to here? Who has greater entropy? This has. But this is more probable. But it is better to show with this figure, then you have more understanding. Follow this diagram. Follow this diagram, all set. Say A plus 2B I am writing. This in context of this reaction. A plus 2B going to this side completely to 3C. A plus 2 start, initial, goes to completion. It can be. It is stuck in the middle where equilibrium is attained. So the figure is like, you see, suppose this is where equilibrium will attain. So I am giving you, this is the initial, A plus 2B either this side or this side. So this is the equilibrium. I am giving you, so this is full 100% C though. So maybe equilibrium state. How much it is? I am giving you, this is 30% C. Say. 30% C. Say. How much C here? Tell me how much C? Tell me. 0% C. And how much here? So it is the journey from this to this, 100% C. C for species. 100% species C is the species. Okay. Percentage C increasing. You are getting entropy. Sketching entropy. If we draw this, you will see this will be this figure. You all set. You understand this. You also this is the S against percentage C. Extent of reaction. What is extent of reaction of the reaction? Happy? So what is this? This is actually this is what, right? This is the equilibrium state I have already written. So this is S max. Easy. So what type of system? Right on the top, constant U, constant V system, and no non-mechanical work. I am writing isolated system. So what has happened here? What has happened here? Actually, this state is equilibrium. What does it mean? Now follow. What does it mean? This is non-equilibrium. I am showing you non-equilibrium, non-equilibrium, non-equilibrium. Okay, this is also non-equilibrium. All non-equilibrium. You can start from this side also. Non-equilibrium. These are non-equilibrium state. Non-equilibrium state. What is the probability of this state? Maximum. Probability of the entropy is maximum. Okay, probability is maximum. That's why it occurs. Okay, and these are less probability. Interesting. It is not the only equilibrium state is there. Very easy. That is the difficult part. Other states have low probability, though, but all the same there is some value. There is some probability. But we cannot distinguish. If it is small, say 1 in million, so we cannot distinguish when 1 occurs. Million will occur. So this is exceedingly larger than this. This is the state. What state? Micro states. Corresponding this macro state, this energy, this is a number of waves. So this is actually, so it will have, so okay, maximum entropy and most probable state. Okay, and these are actually number of arrangements. Okay, say energy arrangement. Okay, yes. Internal energy arrangements. If you see this, you will see actually these are the maximum number of complexions or arrangement distribution. They are less. So this is in nutshell actually what is the probability. So you ask me probability. This is the most probable. Entropy is the most. S max is the most probable state. This is the most probable state. The moment most probable means others have some probability. Yes, admit. So statistical thermodynamics says a small probability. This is the most probable only. But classical says it is the equilibrium state. This will happen. This will be okay. This will have some okay. Some of the what is this states are maybe corresponding to the non-equilibrium, but these are the. This is actually when it is considered Avogadro's number. This number is much greater than this. So this is actually finally which is observable. So most probable state. I think I should not state. Achha, this is one thing I tell you. This is another way. Just outlining so that you have some satisfaction. And this is also in the handout. since I am not touching upon this configuration entropy quickly, but not detailed. It details take time. Okay, maybe actually normally I take home configuration entropy example. Configurational entropy. Quickly, say you see, follow this. So two boxes. Again, consider two box. You have, these are two box. Again, an isolated system. See, no thermal, isolated system means constant U, constant V. Isolated system, constant U, constant V. So you see, four A particles, this side. Quickly I have to write, A, this side 4B, B, this state, initial state, state 1. Okay, state 1. See, this actually now how many ways this can be positioned inside this. What you follow this, state 1, when 1B and 1A exchange their crossovers, follow, position. So what you get, 1B in this side. Okay, why it will get? Say, concentration gradient is diffuse, this will get here, this is the partition. And partition is, so you snap the partition, then mixing, this is a mixing process. I'm writing here, what is the process? 4A plus 4B. Okay, pure 4A on the one side, pure B on the other side, goes to what? A mixed state, a little mix up, a solution, AB solution, okay, 4AB, okay, so 8AB solution. A process is known as mixing. Mixing is a spontaneous process. So what you have done, you have taken separately two components, snap the partition. Now see the magic. Follow the occurrence, okay? Follow the this happenings. Follow happenings. So this start. So B here, B there. Then how many ways this will be arranged? I'm showing here. So this side may be state 1. Follow this probability. What is this? How many? Draw the quickly. I don't have time. So B here. B will cross over. And this side follow. A on B can take position here. Other side A, B. You consider one side, other side will be automatically same. So B can be here, C, configurational. B can be here also. So B can be here also. So I'm writing B can be here, or alternatively, I'm showing how can I show this, or say B here, I'm writing here, B, A, I'm giving you. B here, or say I'm writing here in bracket, taking positions there, okay? Then what I'm trying to do actually, B can be B is here, okay? Acha, or say this, or no, wait a bit. Fix this, yeah, okay, wait a bit. B can be here, it's okay. B here. Not only here. So how many? One is already I showed, others are in bracket. B here means others, here. When B is here, A is here. When B is here, A is here. When B is here, A is here. So four arrangements. Similarly, with every arrangement, so one arrangement, first arrangement. Similarly, this side also similarly happening. A here, or A here. How many? Four arrangements. So 4 times 4 is 4 arrangement. Write this 4 arrangement times 4 arrangement. So it is 16 arrangements. This is 4. With each of these 4, say follow 1, don't change. How many there? We keep this, don't change. How many? 4. Any 4? 1 fixed here. Then change this. Again, how many? For this, 4. Here B. How many there? 4 already. 4. And 4 into 4 is 16. This is giving us 16 arrangements or distributions. 16. I'm very sorry that I'm writing distributions. What is this distribution? We call it omega. How many? I'm writing, you follow this. See, 1 is to, how many A? This side or 3? 3 is to 1. Left hand side component, right hand side component. About A, number of A atoms. Number of A atoms. In left hand side and right hand side given there. So what is this one? Initial one is what? So how many is answer is? 4 into 16 ways. 16. What is this? 4C, how to get this? 4C1 times 4C1, which is 4 into 4. Quickly, okay though? So 1 has crossed over only. There are so many. See, so many B's are there will cross over. So 1. At initial, by the way, what is the initial one? Initial state I am writing, since I am actually showing here. Initial state once more, initial state, right here. Is what? Once more same figure, right? What I drew. 4A, 4A, 4B, 4B. What is this? Initial state. What is how many distribution? Or how to write this? Sigma. Answer this. How shall I write it in this language? 3 is to 1. 3A left hand side, 1A right hand side. What is this? 4 is to 0. 4 is to 0. This is initial state. Has not crossed over yet. Nothing has crossed over there. That is also enlightenment. Probably most of this is also probable. I'm giving you actually most probable will come soon. That's why since I've started, I'll show you what is the most probable. But these are some probability. How much probability I'll give you? Based. What is the arrangement here? Tell me. Can you tell me? These atoms, these are actually indistinguishable atoms. Tell me. Here, how many ways you can arrange this 4A? The indistinguishable. If A is here, how shall I know, sir? One from the other. Same, 1. And other side? 1. So is what? How many? 1 into 1 is 1, and also obtained from the rule 4C0 times 4C0, you know very much. 1 is to 1. 4C0 is 1. So only one initial state. And final state is what? Initial state and final state structure. Final state. Possible distribution in the final state. One itself will be one of them, and the next one already I have shown, and still next I will show you, that will help you. Still next 2 is 2, you will be able to very easily follow me. Follow me again. 2 have crossed over. So B and B, 2 crossed over. A remaining there. How many? 4C2 into 4C2. I will show you this. 4C2 into 4C2. What is this? Omega. How many? Write this. Write this. This is what? This is BB. All there. Okay. AA has been not. A, BB, AA, BB. Is right. Answer is right. 4C into 4C2. What is this? 6 times 6, 36. Okay. How is it possible? What is this? Follow. Why 4? At least I am showing, explaining here. B. Okay. B here. Fix B. Now. B here, this B, then this B here, keeping this fixed, I am giving the expansion for 6, and the same thing will happen. Any of these 6 there, so 6 of this 6 into 6. So one expansion is necessary. So B fixed. B can take this position. What else it can take? I'm showing this position. Then A will go there. Then A will go there. Then or it may take with B. Right. This B. Actually, it is better I write B1, B2 actually. Actually, it is better I can write. Can I write B1, B2 will be better for you to distinguish. B1 fixed. All of B actually. I am writing to distinguish B1, B2. So B2 comes here. B2 comes there. How many? With this, how many? B1 there, fixed. B2, second B, which has entered this side, crossed over, B crossed over. Because partition is snapped actually, otherwise how will cross over ever? Okay. So fixed, how many? B2 can be here, B2 3. With this 3 and B1 here fixed. B1 can take this place, again 3, how many? 12. But if you study well, you will see there are repetition, doubling of this. So it will be 12 by 2, 6. This I don't have time. 6 by 6 also in accordance with the 4C2 principle, 6. It means 6 finally, okay, distribution. And 6, the total distribution, what is this is 2 is to 2. Left hand side, right side, A, in terms of A, okay, is 6 is 36. Now similarly, quick answer, I will not write this. Next is 3 has crossed over, 3A. So 3 this side, 1 remaining, other side. How many? Tell me. 3 crossed over, 4C3 into 4C3. You know 4C3 as good as 4C1. Also there. So 4 into 4, 16 back. And last one is what? All have crossed over. None there. So what is this? Sigma 4 Okay, have I written correctly? I have not written correctly. Sorry, very sorry. If 3 have cost over, how many A remaining here? In terms of A, I have written here, not number of atoms. Number of atoms on left hand side and number of atoms, A particles actually, A atoms or A particles. They use the term particles, okay, some from this particle in a box. In the right hand side compartment, in the other it is compartment. The meaning of this, sorry, actually I have to write this, otherwise mistake you make. Write properly. So yes, so first is 4 is to 0, then 1 short, 3 is to 1, then 2 is to 2. It is very difficult. It will be what, tell me? The 3 left hand side, 3, 1 only remaining, 1 is to 3. 1 is to 3, 3. 1 A this side 3, and last one will be non-A, all has gone to the other side, 0 is to 4, it will be 4C, 4C3, 4C2, 4C4 times 4C4 is as good as 4C0 into 4C0 is 1 into 1. So total distribution, so let us complete this. Sorry. So total 37, 38. So total distribution, remove this, remove. So total distribution, tell me. Now you will understand what actually happens according to the statistical thermodynamics. Statistical means, so total distribution of the mixed state. Of the mixed, you have asked to mix. One is unmixed. Initial state, like initial, don't, what is this, right? Unmixed. Unmixed state. Because I have not snapped. This is partition snapped, so the partition snapped. Partition snapped. Unmixed. What is the process? What is unmixed? Which is the unmixed? 4A plus 4B. What is unmixed state? Initial. Initial is the unmixed at the left hand side. This figure. Okay. This goes to a mixed. About mixing, so many complications. Mixed state, all are mixed. So a mixed state is this 8 AB solution means why 8? 4 atom, 8 atom. Okay, right this way. Oh, actually it will be so you call it, otherwise it is difficult. 4AB is better. 4A, 4B, 4B. Okay, this is better. 4A, 4B, 8. Quickly, so total distribution of the mixed state. What is the distribution? Tell me. How many ball? Tell me. Mixed state. How many? Tell. One by one. This is also part of the mixed state. Mixed state, it is not always moving from one to another, transiting from this to this. So here. All 4 crossover, none has crossover. These are the kind of mixing. These are possibilities. Very low probability. How much probability? 1. Out of total is what? Write this. Then 1 plus what is it is? Next is 4. 16. 16. Still next is 36. Still next is 16. 16 plus 1. This is 70. 70 arrangement. 70 arrangement. Total number of distributions. Okay. Total. So this can be obtained also your factorial 8 means 4 plus 4 is 8. 4 plus 4 is 8. Factorial 8 divided by factorial 4, you get this number. So now you understand what is the most probable accessor of 70 total distribution. What is the contribution of this? This distribution how much? 1 out of 70. So if you take 70 inspections or 70 observations, you will see 1 of the 70 observations is likely to be this, and 16 of this will be likely to be this, and this will be like 36, which is the maximum distribution, 36, and this is the most probable. You ask me, what? So in a mixed state, what is the most probable? This one, 2:2 I have written somewhere, 2:2. 36 is the maximum. This looks actually not very large, but when you consider Avogadro's number, the number difference is much greater, and you can neglect. So this is the most probable state, equilibrium state. You might say, what is the equilibrium, sir? What is equilibrium? This is equilibrium also. Why? This is actually 2 atoms of A, 2 atoms of B, 2 atoms of B, 2 atoms of A, eliminating concentration gradient. Is there any concentration gradient? 2 out of 4 here. Percentage of A is what? 50%. This component. Where I have done this, where I have done, here I have done, here, correct, correct. See, this is, follow, see, how many, out of 4, 2A and 2B this side. What is the percentage? 2 out of 4 means 50%. A, 50% B. This side, 50% A, 50%. So, no concentration gradient with respect to A or B. So, equilibrium state, sir. So, this is equilibrium state, but they use the term most probable state. Means, you could make observation, see, sir, equilibrium state only this. No, no. Most probable. There's limited probability. This is all about this. Okay, but still I am not covered. You refer to this because this should be considered in terms of a proper solution. I am giving the outline. Instead of 4A, this will be later on. This will be later on. NA plus NB. Pure. This is generally speaking. Later on, generally speaking, write this. Generally speaking. A mixing relation, a mixing process. Follow this part. Na moles of particles of A plus what? A is what? So solid solution. So this is mixed solution, liquid solution. Na a solid I am not writing. Plus Nb of B. This is what state? Tell me. Goes to Na. Plus, okay, what is this? Na plus Nb, this should be, okay, this is Na plus Nb, okay, what is this? AB solution, okay, AB solution, let it be there, okay, don't worry, this Na moles and Nb. This is a solution made up of Na moles of A, Na moles. Solution means, in lattice, they undergo into the one phase, single phase. There are two different phases. Unmixed, what is the state? State 1, state 2. This is what state? Unmixed state. This is mixed state. This is solution state. Let us see. You tell me, classical, you tell me. Suppose not here. See here. Delta is what? Delta S is what? Where I wrote this. Delta S is what? S2 minus S1. Okay. Okay, S2 minus S1, okay. What is this? S2 minus S1. What is this? Okay. KLN, what is this S2? Tell me. KLN, second statement, final. KLN. Please tell me. I will be very happy if you keep on helping me. KLN, what is, how many second step? How many? Second state? How many configuration? Omega. Second state means the mixed state. Second state means the mixed state. 70. KLN 70. KLN 70 minus KLN how much? Initial state is one of the possibility. So it is initial state as well as one of the possibility, least probable state. So KLN 1. So KLN 1, you know, what is this? 0. So KLN 70 is the answer. So in this case, please tell me what is the KLN, what is the answer? I am writing for you. Delta S is what? KLN. Can anyone answer me? I will be very happy if you answer me. So this is for our problem. Sorry. This is okay. This is already done. What is the answer? In this case, Na, not 4. NB, not 4. What is the answer? Again, similarly, 70 comes from how? Oh, there. Okay, what is that? Factorial. We don't use this term, this symbol, Na plus NB. 8 means 8, 4 plus 4. Factorial divided by what? Na factorial, NB factorial. And there is a nice rule. Can I start this? Remove all else. All. Triple star maybe. Remove all. This remove. All over. Since actually I started this, kind of some satisfaction that I have already at least touched upon this. This triple star, there is a nice principle, a nice equation. Starling's approximation. You know what is that? You will be very happy to understand. See what it is. By the way, can you write this? Can you write this? First of all, let me write. Okay. Delta S is what Delta S is what? Please write this. KLN, right. Break this. Break this. Log means you know log means log, you know, Na plus Nb factorial. Minus, tell me, k outside, minus ln Na factorial, sir. Minus ln Nb factorial, sir. Happy? And give a box. This is the factorial. Factorial is factorial. Factorial. Starling's approximation is what? You know factorial, you know. Log factorial, log something. Log factorial something, you know. Factorial 4 is 4 into 3 into 2 into 1. Log 4 factorial. So, ln x factorial. Rule is what? Approximately when x is large. This Avogadro's number of particles we deal with, so it is large and suitable. X ln x minus. This will be. So, if you write this, what it will be? I will not go at length. X is what I do here. Na plus Nb. Okay. Tell me x ln Na plus Nb. Minus, tell me x again. X means Na ln Na. And minus Na means plus Na. Again, second is what? Minus this one. X ln x minus x. Minus I've taken perhaps. Take a look. Please follow this. What is this? Na ln A minus Na. Or minus that. Ln Na, follow here. Na ln A. And minus outside. So, fantastic. And then what next? What is next? Minus Na. And minus there, plus Na. Huh? Oh, you right, very good. X ln x minus, good boy, very good boy. I'm very sorry. Achha, I'm skipping actually, I'm moving fast. Minus Nb ln Nb, good, very good. Will you be happy to do this? This Na minus Na plus Nb and this plus Na plus and get rid of this? Why not get rid? Get rid as soon as. The minus is anywhere. No minus though. So far, k ln. What is this? See, I'm taking Na. Follow me. Minus Na common. Follow minus Na. Follow this term minus Na. What you get here? ln Na. Where you get Na? Another Na. This one Na. This is Na plus Nb though. 2 Na ln. So if I take minus, this comes down. So minus Na is so ln. What is this? Ln. Tell me Na plus. Oh, good boy. Sorry. Ln. What I get here? Minus Na ln Na. Minus become plus and this becomes minus. Na plus Nb. Take a look. Take a look. This term, and this term. Nb subtract Nb. It's okay. Everyone okay though? See this term and this Na and this. Then similarly, minus Nb ln Nb by happy minus outside, take outside by all means ln. This is actually mole fraction. Number of atoms of A, total number of atoms. That is the mole. Number of moles of any species divided by the total number of moles. How many? This is the mole fraction of it. So write another line Na ln Xa minus is common. Nb ln Xb happy. You will have, this is for how many particles? Valid for how many? Solution how many? Okay, this is actually delta S. This is known as what? This is known as, I have written where? Delta S. This is known as the mixing process, right? Delta S mixing. Delta S, what type of process? Mixing process. Pure goes to impure. Solution is actually part and parcel of our life. Iron plus carbon solution. This minus you take common. Minus, both are minus, so I am taking outside. So become plus. This is outside minus outside. So then both are plus, okay? Minus 4 minus 5. Can I take minus common? minus 4 minus 5. Can I take minus common? Then what it will be? Minus common. What it will be? Next, what it will be? What it will be inside? That I have done. Oh, that principle is principle. Okay, always whatever. 4 log. Okay, minus 4 log x minus 5 log x. What it will be? What it will be? Again minus common. What will be inside? Will be what? Parenthesis. Both. Minus 5 log x. 5 log y. 5 log y. What will be minus common? What will be inside? Tell me. 4 log x. Whatever is there, just strip minus.
Yes, sir. ln
This is x-ray. This is x-ray. This is x-ray. Huh? This part is x-ray. This is no longer there. ln x-ray. So minus na ln x-ray minus out. Ln x-ray. Okay. So valid for how many? For Na plus Nb particles. For 1 gram atom, can you tell me anyone? For 1 gram atom, this is K to R, K is a Botzmann constant to Avogadro's number. Who is separated by? Sorry, K to R, universal gas constant and K. How they are separated? Avogadro's number. Na? So for 1 gram mole, 1 gram atom or gram mole, or 1 gram mole or gram atom. Na? So mole you don't use such 1 gram mole. What is this? For Na by particle, K by for 1 gram mole, Avogadro's number. Usual method. Good boy. Oh, this you said. This you are asking me. Yeah, they are perfectly correct. I should have not written this. Now this is wrong actually. This is first place wrong. This is good thing that you are actually helping me. This is a very good thing that you are helping me. Right? Perfectly right. Unnecessary, meaningless. Okay, so it's okay though. So you have to follow me. For Na plus Nb solution, particles, solution molecules, solution atoms, for 1 gram atom. We talk of molar, 1 gram mole. So for 1 mole is this by unitary method. Then inside is what is this? Well, K times N is what? K times, good boy, R. And then at least follow me. I'm writing. Follow. This is here. Na by Na plus Nb I am dragging. This I dragging inside. Na by Na plus Nb plus Nb is there cross ln x-ray. Someone is actually loitering. Hello?
Sir,
5 minutes, okay. What is this? Minus Na by Na plus Nb. Tell me this side. Tell me. What is this? See, Na, follow. This is, shall I write this? Oh, Na ln x-ray. Write this. Plus Nb ln. See, don't mix up with x and n. One is n, another is x. N is the mole fraction. Number of atoms, particles. Na by Na plus Nb. Are you happy? And this will be what? This is what? This side, the second term will be what? Somo, second term, this is first term. What? Are Baba, drag it inside. Oof, it's difficult. It is natural that you will do yourself. Why you will do yourself? Can you tell me? Yes, Somo, why shall I do this? Oh, x-ray. That is ln x-ray. Oh. Why I shall do this? I say you drag it. Why? Move first. Nb by? Tell me what? N. Actually, N. I see this one. Stop that. What is the name of this? A moment ago. What is the name of this? So what is the answer? Minus or famous relation. This is famous entropy of mixing. This is to your satisfaction, to our satisfaction. So delta S M classically found, or thermodynamically statistically found. Statistically found, or delta SM is delta, delta SM is delta S is what? This is configuration, delta S configuration, right? Delta S is delta S configurational. This is no thermal I have not considered, okay? Because okay, this is only configuration, the thermal there is no change. Ideal solution, etc. Don't worry, this part is what? Answer. Famous relation, minus R, XA ln XA plus XP ln XP. Thank you, and very much thank you, right? Is this box. Famous relation. This is also classically, it is interesting to note, write this out. It is of interest to note that classically that we obtain the same relation, exactly same relation classically. It is not and very satisfying also. It is of interest and it is of same relation classically. Classically, actually, when you study solution thermodynamics, then we will find out this. So today you found this. This one. Yeah, valid for Na plus Nb particles, because Na plus Nb we started with. We started with NaNb, but we want to upgrade to 1 gram mole. Oh, valid for what? This is valid for what? You didn't say this. This is valid for how many particles? Na plus Nb? 1 N particles. Valid for N particles. That is, tell me, that is 1 gram mole. You write this molar right here. Same is molar entropy change. Entropy of mixing for 1 gram mole. 1 gram mole, about molar entropy of mixing, exactly. Molar entropy of mixing integral, molar integral. So you see there are number of terms are there. It is of interest. Classically also. Okay, this actually you would study when you study solution thermodynamics. I do not know when it will be. Integral. Molar integral entropy of mixing, right? Molar integral. So I am writing here. Molar integral entropy of mixing. Why integral? Why integral? I tell you. When this is partial, you are asking me something. Integral is opposite to partial. Partial when about A, only A and only B. So this is if you ask me what is the partial, sir? R ln X is the partial entropy of mixing for A. Partial means you have to specify for which. Minus R ln X for parts. Okay, this is partial entropy of mixing, partial molar, and minus R ln XB, partial molar entropy of mixing for B. Then when them together, integral. And what is the weight? It is partial 1 mole, but how many moles are present in 1 mole? A, how many moles of A in 1 mole? X is mole fraction is the mole, then total is 1, means X is the mole. So for 1 mole minus R ln XA, for XA mole multiply integral, molar integral entropy of mixing. Okay. Hold on, this part. This is over with this. ln X is X ln X minus X. Starling's approximation. Starling. Stalin is a man, okay, human being. Okay, he is actually mathematician. Sorry, is a man. I said ln x. This is what this is factorial. Ln x factorial. Factorial. This is another symbol. Okay, with this we have actually already lagged much. Okay, but at least so you have got the probability, and you have also asked the probability. This is clearly understood from this. I'm sorry, I have to stop this. So let us stop. Okay, today we have enough of discussion. We'll take up next class Monday. Okay, thank you very much.